We are recording. Good. Okay. Let me just check that everything is okay. And I've just started recording.
It's recording, yes.
It's recording.
Yeah. Sound is okay.
Okay. All right. So yeah, thanks. Yeah, everybody for being here again. So we're ready for the second round. To can you summarize what happened last time? So what happened last time is that syntactic objects are a magma and workspaces are a Hopf algebra. This is the punchline of what happened yesterday. So now, what we want to do with these workspaces is to use them as the input for merge operations that give you derivations of sentences. Okay. So I have to describe the merge as some action that's taking a workspace as input and producing a new workspace as output. All right, so let me first describe what merge, how the merge action of workspaces is usually described, and then say a little bit more how you phrase it in the Hopf algebra setting. So so first of all, you think of merge as a family of operations which are labeled by a choice of two syntactic objects. So you have like a family of operations as S and S prime are two syntactic objects. You have an M, S, S prime for any choice of two syntactic objects. And you take an input workspace. So your input workspace is a forest that has several tree components. So each tree is a syntactic object. So it's your collection of syntactic objects. Okay. And what this merge operation does. So first of all, it searches the workspace, and what it means that it searches the workspace, it means that it searches all the accessible terms in the workspace for terms that are that can be identified with S and S prime. Okay, the terms isomorphic to S or S prime. And then when you locate a matching term, so you locate an accessible term that looks like S and an accessible term that looks like S prime. You pick those two accessible terms, you merge them together using this merge operation of the magma of syntactic objects. So these now are two syntactic objects. So you can apply this operation and get a new syntactic object. And this new syntactic object is now added as a new connected component of your new workspace. And then I have to say what happened to the rest of the workspace, right? So these two accessible terms that I found that look like S and S prime were somewhere. So they were in two of the components of the workspace, maybe in the same one, and two different ones. So what I do is now, if I've created this new object, now I have two copies of these syntactic object I'm using. One has gone into this new component, and two wherever I found them. And now I cancel the default that I found, and so I keep only what's left of those the two of the places where I found this my syntactic object I used, and everything else in the workspace that's not been affected by this operation remains the same. Okay, so this is the usual description. So I'm calling, so if F is my initial workspace, I'm calling again F hat, whatever is left, whatever was not affected by this action of the merge, that remains the same. And then I have the new component and I have the other. So, okay, this is the usual description that you find in the merge and start meaning on this easy spoke, and that's fine. So summarizing, it's like what I wrote in the first line. You take that, the new workspace F prime as this new component, has what is left of the places where you find this two accessible term, and has everything else that's not untouched, that doesn't involve these terms. the notation that I defined in this book is slightly different than the one that I'm using, but it's the same. So if I want to write this in terms of, this algebra structure that I was describing yesterday, I can do it like this. So I can say the first thing that happens, so I'm writing this formula in this line. The circles are composition of operations. Okay? So it means that you start reading it from the end. That's the first thing you do. Then it's composed with the next one and so on. Okay. So I start at the very end. The first thing that I'm doing is, applying my coproduct of the algebra. Why I do that? Because that produces for me the entire list of all the accessible terms of the workspace. So when I start with the workspace, I have the components, but I hit it with the coproduct, and the coproduct produces for me the entire list of the accessible terms. So that's the first thing I want to do, because that's where I'm going to search for something. So I have now the place where I want to search for the things, the material that I want to use for the merge operation. Then the second thing I do is this thing that I'm calling delta. So this is where the datum of these two syntactic objects that I want to use is involved. And this is where I search for matching terms, right? So I have my own list of all the accessible terms in the workspace. And among those, I look for the matching. And whenever I don't find anything matching, I leave what is there and I don't touch it. But if I find matching terms, then I do this other operation that I write there. So notice that this operation is really doing nothing on the right side of the coproduct. It's doing something on the left side of the coproduct. And the left side of the coproduct is the part where I'm extracting the accessible terms. The right side of the coproduct is where I have what it is left. So the right side of the coproduct at the end of the story is only doing the cancellation of the deeper copies. So I'm not merging anything there. It's just keeping track of what is left after I've done the merge. The merge I do on the side where I've extracted the accessible terms that I can use to do the merge. And so what I do is, I have an operation which a priori is, not necessarily binary. It's some operation which is just called the grafting operator that takes a forest and hangs everything together from one point. Okay. And so, of course, because I'm looking for something that I first hit it with something that will only look for a pair of terms. All the other grafting operators that involve more than a pair of terms will not do anything. So will only end up with the case when this has two terms. So I do this merge operation that produces the new component of the workspace. And then, so the last thing that happens in this formula is that I'm applying the product. Okay. So why I'm applying the product? Because now I'm recombining all my pieces together and putting them together to form the new workspace. So the last operation, I'm putting together the new workspace, which now is going to have, what it's going to have in it is exactly what I want on the first line up there. There's this new component that I have formed with merging the two accessible terms. And there is everything else that I have left, including all the things that have not been touched by the merging. Okay, so this is just a way of writing as a single line what you say in Word as this sequence of operations. All right, so this is how I'm gonna describe
Question.
Yes.
Just in the definition of the graph operator, the T1, T2, Tn arguments there, those are the structures you get from putting together the matching pairs of accessible terms?
Yeah, so remember when I talked about how you do the coproduct, right? If I take the coproduct of the tree, I'm going to end up with something that has some forest of that whatever I cut, right? So
Yeah.
I get a bunch of things, so this is gonna be some T1.
Okay, right.
T, okay, yeah.
Right,
And on the other side, I have what is left when I
right.
contract this, right? And so I'm saying now, I can make an operation that takes any
You just make
forest
it a
I
single
have
structure.
and just,
It turns the
attaches
forest into a
everything.
tree.
do a single root.
Yeah, okay.
And now, this is in general not okay, because, I'm dealing with binary trees, and this is
Yeah.
usually manufacturing not a binary tree. But, if I'm only applying it to the case where I have two things
Yeah,
here, then I'm good.
right, that's what the delta's gonna
And
be.
that's because I'm already selecting only, so in principle, my coproduct has a lot of stuff. And I said, before that you do need to have a lot of stuff in the coproduct if you want the coproduct to have nice algebraic properties, like this co-associativity property.
Right,
But when you hit it with the search for matching terms, you're searching for a pair of terms. So you will not, you will not see the other terms
Got it.
that would give you this analytic ones. Okay.
thank you.
And there's other reasons, that why it's kind of a natural to write it in terms of this operation that I write as beat and so on. It's this is just an aside, but as I said, some of these algebraic structures have manifestations in different contexts. And this operator that I write as beat and so on is a well-known thing in physics that does exactly this operation in exactly a similar situation. And there, of course, you do need also the analytic ones. But it's kind of, so that form that this operator takes is something that's kind of familiar, looking familiar in other settings. Yeah. Okay. So, so I'm describing it in this form. Okay. So now one issue that arises is that when I describe it in this form, I get more cases of merge than what I might want to have. And so in particular, I can sort out a few different cases, and which are listed like this. So as I said, you're looking for a pair of accessible terms of the workspace. So one case is that both of them are entire components of the workspace. And another case is that, for example, one of them is an entire component and the other is an accessible term of that same component. And these two are the ones that correspond to external and internal merge. But, in principle, the way I constructed this also allows for other possibilities. For example, one could be an entire component and one could be an accessible term of another component. Or both of them could be accessible terms, smaller accessible terms of two different components. And these are all the cases that happen. The two remaining cases that I listed, which are not external merge and internal merge, they usually go in the literature with the name of sideward merge and counter-secret merge. And there are reasons why one might want to eliminate this, because they do give constructions that are not always linguistically viable. So let me start by describing the two cases that we definitely know we want. So external merge and internal merge. So just to see a little bit more closely how they function when I write them this way. Okay. So let's just look first at external merge. So I'm using the same example that is in this book on merge and the strong minimalist thesis. So, because they also introduce the external merge operation. So suppose that you start with a workspace that has two terms in it, so two connected components. One of them is a single leaf with a label, with a lexical label. And the other is a cherry tree with two leaves and with the corresponding lexical labels. Okay. And of course, I want to merge these two. I want to do the external merge of these two. So how do I do it with the formalism that I just described? So first, I take my workspace and I hit it with the coproduct, okay? So I hit it with the coproduct, it's gonna have the sort of trivial decomposition that in which I'm not splitting it apart. And then I have the various ways of splitting it apart. So actually, in a sense, no, the first line is all part of the trivial decomposition in the sense that it's the one that I described last time, that if you, where the syntactic objects themselves are indecomposable. So here you have two syntactic objects, and so all the decomposition where the syntactic objects remain indecomposable are either the whole forest is not composed, so the first two terms, or the two objects are separated, one on one side, one on the other side, but they're not decomposed themselves. Okay, one of them is a point, so you cannot decompose it, but the other one you can. And so the remaining terms are the ones where you decompose the one that can be decomposed. Okay. So the coproduct is all of these possibilities. However, in this case, the one that you want to use is a very simple one. And so here's the same. So I'm just writing the same two lines with the explicit lexical items. So I have all these terms of the coproduct. And of course, because I want to merge two terms, and I know that they're going to match the first term. The first term of the coproduct here is enough, the most trivial one, because my external merge is extremely simple in this case. Okay. So my thing that looks for matching terms and selects the matching term finds that the first term already is okay. So I just pick that term. And now I get that term in my grafting operation, which means that I take these two components and I append them by the same root. And I get my external merge. Now, you see, on the other side, I don't have anything because this workspace was extremely simple and it only had these two things that I wanted to use. If it had a lot of other components that were not touched, I would find all the term that I would use would be the one that have all the other untouched components on the other side. And so when I recompose with the product, now the term on the right doesn't do anything because it's the unit for the product. So I only get what I get. If I had other components that were not involved in the merge, those when I recompose my new workspace with the product would appear again as components as they were at the beginning with no effect. Okay, so that's what this final product does. It recomposes the workspace. All right. So what about internal merge? So internal merge is a little bit trickier to describe in this form, but it's I'll say in a moment what you do, which is something that in the end doesn't look. It's simple. I'll check that it does exactly the same thing that we want it to do. Okay. So one comment here that of course we have this element, right? This formal element, which is the unit for the product. The product is the disjoint union. So the unit with the disjoint union, if you take a union with something and it has to be the same thing, that's something that you're adding is empty. So your unit for the product is the empty set. I just keep track of that. It's just a way of saying there's nothing left in your workspace. You used all the components that you wanted to use. So it's a marker for keeping track. There's nothing else to worry about. Okay. And these things also happen to be the unit for this merge. What is it? It's also the unit of the magma. So this magma operation, if you attach nothing, you're left with what you have. Okay, so this is a small observation that actually now made in several places already, that this internal merge almost looks like the successor function of arithmetic. It's not quite that. So language does not contain arithmetic, but it almost does, in the sense that if you think of the von Neumann construction of the integers, so you start with the empty set, and then you have the set that contains the empty set, And then you have the set that contains the empty set and the empty set and so on, right? So after that first step, everything is an internal merge. And except the first step from 0 to 1 is you need a unary, not a binary merge. So that's the only way in which, you know, it does not contain arithmetic, because you don't have the unary merge. You also have the binary merge. Okay. But so essentially internal merge is kind of like the successor function of arithmetic. But the observation I'm making here is exactly because, you know, at first it might look like it to take this merge with the unit in Gen 3, it should do something like this unary, but it's not a unary merge because it's the identity. It's not, I mean, the unary merge would have to give you something new. So going from 0 to 1, you know, here this is the identity. So there's this. Okay, so what do you do when you do internal merge here? So you do basically two operations, right? You first consider a merge where you take one accessible term and this unit. And what does that do for you if you apply this list of operations that I just gave you? It extracts an accessible term and puts it in the workspace together with its, you know, its corresponding term with a deeper copy cancel. So this is just formally an operation that makes it's what normally is, you know, in the linguistic paper is copying something into the workspace, copying an accessible term into the workspace. And then once you have this accessible term and the corresponding in the workspace, you can apply an external merge on the two of them and form what the result of the internal merge is. Okay. So the internal merge, you can think of it as being the composition of these two operations, that, you know, placing an accessible term in the workspace and then merging it with the other one where the deeper copy gets cancelled. Now I'm saying that this single operation by themselves that puts an accessible term in the workspace, you don't really want to consider it as something that exists in isolation. It's only part of your internal merge. The reason for that, I'll say it in a moment, because you want some kind of you know, rules on how your merge operations act with respect to the size of the workspace. You don't want to keep adding things to the workspace. This is added just because altogether the operations then puts it back into the internal merge. Okay. I hope this is nice. Okay, yeah.
So one I hate to use the term psychological here, but one consequence of this is that one of the driving forces for syntactic representation is this binary rootedness of forming a syntactic object, right? So you don't really, it doesn't need to be binary rooted, but the way you guys have formulated it, right, is as a binary tree. So there's a claim about syntax that a lot of this follows out from the fact that they're considering these binary rooted trees as the primary structure, as opposed to.
Yes, yeah, so that's right. So I'm gonna come in a moment to discuss why, you know, so you can say, what if I have also a hypothetical NRE merge?
Yeah, okay.
Right.
Okay.
So I'm gonna discuss it in a moment. So I'll tell you the answer right away. When you discuss it, if you do, you find that both under-generates and over-generates with respect to the binary merge. So you both lose some of the constructions that you have from the binary merge, and you get unwanted one at the same time.
Yeah.
And you can actually quantify exactly by how much it under-generates and by how much it over-generates.
So in the case where you just have unary merge in this sense, where then you get PNO arithmetic is clearly an under-generation issue, right?
Yeah.
Or sorry,
Yeah,
over-generation, right?
but I'll discuss it in a second. So yeah.
So I just want to try and understand internal merge. So my understanding of internal merge is that it's sort of a two-step process of the merge you've defined, right? So the first step will find the beta and as an accessible term, and it will merge that with the unit, put it in the workspace, and then you would take that thing, or, you know, then you can merge the beta with the leftover when you've taken out the beta.
Right.
So
Yeah,
two-
this is sort of, yeah, I
Yeah.
mean, if you look at how it's described, normally,
it,
right? It's because it's like you do this.
You have to
this
take it
kind of
out.
External, you have
and you
to take
put
it
in
out,
there,
and then
and then you can use it.
yeah.
Right, got
Right,
it.
so I'm just describing that. In
Okay.
fact, the thing is, you shouldn't think of this as two separate operations, right? Because in a
Right.
sense, I'm gonna come to, like, when you do this selecting of, I'm trying to tell you in a moment how you end up selecting only external and internal merge. And the way I'm gonna do that is to actually say, you pick everything that's of degree 0 with respect to some grading. And these compositions will end up being of degree 0. So you think of them as being like one operation.
Okay. Okay.
Okay, so let me just go through an example. Okay, again, I'm using, I'm trying to use always the same examples that are also in the version from minimal this thesis book, so that one can see exactly how they match with the different notation. So, now use the same example that we had before, the apples, so now this is formed as a syntactic object. We start with a workspace that has a single syntactic object in it, which is this tree, the apple. And now we wanna do the movement, right? So we will take the apple as you turn out and you merge it. So we wanna do this merge with these two objects. So as I said, I think of this as being first, taking out this accessible term and then merging it with the remaining part. So I think of it as these two, this composition. So let me just notation. So when I take the coproduct, so I'm not going to write out all the terms of the coproduct, but when I take the coproduct of these three, and then I look for terms that match the ones that I want. So I end up with a term like this, which is the term that I want to extract, and the rest. And I think of it in this form. So I get a new workspace. This is the first operation that I said. I get a new workspace which now has these two components that now I want to merge together. And the next step is I merge these two. So this does what is expected to do. It matches the same derivation that's described in the usual way.
And then when you have crossed out here, the apple set there, it's no longer in the tree, no? Like it doesn't have a location anymore. I mean, yesterday you said like it has a little trace element.
Yeah, exactly. So here I'm using this, so as I said, you can use two forms. So the one, if you want to keep explicitly the trace, and then you want a labeling algorithm for how to label that. But here I don't need it, right? Because this is just a simple, so I don't need to keep track of this labeling.
Right,
So I can just use this version of the coproduct, but I don't keep this trace.
sure.
And okay, and so, the cancellation, what is usually written as the cancellation of the deeper copy is exactly the one that's produced by the right channel of the program. Okay, so now, so these are the two good guys, the external merge and the internal merge. And now, how do we get rid of the bad guys? And so,
Could I just say something about the internal merge? I think a nice property of this formulation is that because we're forming the quotient to delete the inner copies or deeper copies. I think we derived the facts that in what's called remnant movement. So when you move something out of a constituent and then you move the constituent that originally contained that constituent, when you actually pronounce such a sentence, the constituent that was first moved is not pronounced as high in the tree as was predicted if there were a full copy in it. It's So, for example, if I said like, how likely is John to win the race? And, if you're here, suppose that, John is, underlyingly merged with likely. And so, but what we find is that we don't find John pronounced with likely.
Yeah, so if I understand correctly what you're saying that it's not just with internal merge, that I have also these, relations where I have, sorry, I have copy relations.
Yeah.
Yeah, I'll come to discuss that
Okay.
a little bit later. And there is indeed something where you have to account for other kind of situation. So the kind of situation where you have copy relations that are produced by internal merge, you have this phenomenon that the deeper copy gets cancelled, which is automatically taken care of by this coproduct.
Yeah.
But you are right that there are other situations where you also have copies relations and you want to make sure to know like which one, gets cancelled in the sense that you're saying that, only one of them survives when you gather the family of something. That requires a little bit more, stuff that I hope to come to that a little bit later. Because, you have to kind of enforce certain, copy relations for doing that, which are not just accounted for by the internal merge.
Okay.
Yeah, thanks. That's actually a point that, hopefully I'll get to that. It's a little bit later in my slide. Okay, so let me get to the other forms of the merge that we don't, necessarily want to have. And so usually, though this is discussed in the following terms, that you think of some kind of economy of computation, argument that tells you that, the cases of internal and external merge, when you are, there's a stage where you have like all your possible accessible terms and you're searching through them. What is the most efficient way of searching through them? And, the argument is, well, obviously the first easiest thing is I just search my entire components and I look at whether there are just components that match the term that I want to use, and that gives me external merge. And the next easiest thing is, I first search for a component. If I find one, but I don't find a second component, I start looking inside the terms of that component. And that gives me internal merge. And the rest is like less economic with respect to this. So, as a mathematician, this got me a little bit worried because, we said, okay, in what sense is this true? I mean, the first thing I'm 100% on board. The easiest thing you can do is just search whether you have two components that match. The second thing let me explain the thing that first got me worried. I mean, the bottom line is that you don't have to worry, but the first thing that got me worried is something like this. Suppose that, I'm in a situation like this example. So my workspace consists of two components. And when I search for the matching term, the first matching term that I find is this first entire component, this very big one. And my second term that I'm looking for to match is this smaller thing. But I have it in two places. One of them is very deep down into this very big component. And the other one is very near the top of that smaller component. And I'm trying to convince you that searching very deep down this big component is more economic than finding that near the top of the other component. So I have to try to sell you this idea. Okay, so let's see if I can convince you that. So if I want to say that this is the case, I have to come up with some kind of cost function or something that will work, that will make searching very deep down into this tree more economic than searching near the top of the other tree. Okay.
Is it because we should, without it, we should prefer tree two, or because it's kind of, we don't care which one we take? Like, we want to just prefer tree two in favor of T one, or we just want to say, I would happy if we both?
Yeah, no, I'm just taking the case where, no, so you have to find two given syntactic objects, say. And I'm just taking the case where the first one you find, and it's in, so I'm saying, okay, the first thing you do is you search for components, for all components. So the first one, I find it that it's an entire component, but it's a very big one. Right? And now I'm looking for the second one. There's no component that's equal to that, but there are two possibilities of where I can find the second one. Like one of them is like very, very deep down into this first component. And the second one is very, very up near the top of another component. And I'm trying to say that this first one is preferable. It's not very intuitive, it's some kind of counterintuitive, right? So in what sense it's preferable? Okay. All right, so let's see in what sense it's preferable. So I have to give you some kind of estimate of cost, right? So my selection of accessible terms is given by the terms of the coproduct. So if I want to say that you know, I have to assign some kind of weight to the terms of the coproduct, so that some terms of the coproduct weight a lot, and some terms of the coproduct are weight much less. So I'm going to assign a grading to each term of the coproduct that depends on the parameter. And when I tune that parameter, I can make these terms, everything depending on the exponent, right? I can make some terms become very large and some terms become very small. And so I can say which are the leading order terms. This is like a typical thing, or if you think there's physics problems, you usually want to find some viable approximation, and you want to say what is the best approximation. I try to weight my terms in a way that scales, and then I look at the limit of the scale, either when my parameter goes to 0 or to infinity, and what remains is my leading terms. Whatever is of lower order, I can neglect. So I'm doing the same type of reasoning here. And so what is the leading order terms? So the coproduct comes as two channels, right? So I have the things that I've extracted, and I have the things that I have left. And so in principle, both of them carry some weight. And these two weights could be independent, completely independent. So in principle, I'm writing it as two different parameters, this epsilon and eta, how I want to weight, how heavy is the thing that I'm extracting, and how heavy is the thing that I'm left with. And it's clear that the depth of the tree has to play a role. It's natural that searching very deep into a tree should be more costly than searching very near the root of that same tree. So there has to be an exponent that depends on how far I am from the root of the tree. And if I'm extracting, so my coproduct has extracted several components, like several accessible terms, I have to count how deep each one of them is with respect to the root. Okay. So that's why this exponent d is just counting the distance from the root of the various accessible terms that I'm extracting. Okay, now, however, it's sort of strange that these two terms, what I've extracted and what I'm left with, the two weights that I'm putting to those should be related. And I'm arguing that a very natural way in which they could be related is that they are related in an inverse way to each other. Right? If I'm fishing out something very deep, it's expensive to do that. But once I've removed it, what I'm left with is very close to what I had to begin with. So that is not very expensive. I've done a very small modification to what I'm left with. So that should be something that's very inexpensive, right? So I'm weighting these two in complementary way. And the thing is, if you do that, and then you take only the leading term when this weight parameter goes to 0, the only things that survive are the external merge and the internal merge. So those are the leading order terms with respect to this cost. So indeed, that example that I made is true that it's less expensive to search through this very deep thing inside the same component rather than for one in another component, because, you know, if I do searching in the same component, I'm exactly compensating the cost of the extraction of a very deep term with the weight of what remains. They exactly match each other. But if I'm searching something else, they don't match each other anymore, and so I'm left with something that's gonna be, you know, unbalanced in my weight. Okay. So this is how I see what it means that minimal search is minimal. At least it's a way to justify the minimal search is indeed minimal with respect to some cost function.
Do we assume that that cost function is gonna have a unique minimum? I mean, in the sense that you could imagine two terms whose cost is probably exactly the same, right? And all else being equal, we wouldn't have any way.
Yeah, so you could have accidental cases where the weights are equal for accidental reasons, but those are kind of rare.
Yeah.
Rare instances. If you wanted this to be, so the thing is, if you want to think of extracting the leading order term as a function, right, then it has to apply to all. So accidental cases where the weights might be the same, that's.
Okay, so we allow that, but it's
Yeah.
rare, okay.
So why does, if the depth matters, so what is happening with the weights that prevents the shallower subcomponents from being favored by merge over the deeper ones, even within the same tree?
If you are in the same tree,
Yeah,
like, so if you are in the same tree, then by the way, I'm weighting like the thing that I extracted, the thing that I've left, the weights exactly cancel each other out.
okay, so the depth won't make a difference.
Yeah,
unless you're
then it
looking-
won't make a
unless you're
difference,
looking-
exactly.
Unless you're looking across trees.
Yeah, but if I search somewhere else, then
Yeah,
the weights are not gonna be.
They're not gonna be balanced, right?
Okay, so usually there is another argument that is given for the why external and internal merge are preferable. And this is an argument that, you know, if you look in the emergence from minimalist thesis book, is referred to as a resource restriction or minimal yield. So it's something that has to do with checking what happened to the size of the workspace when you do your merge derivations. So these look like two different arguments. And actually, I don't know if I'll get to talk about that. No, it's in my slides later on, but there is a way to see that they really are not different arguments. You can phrase it so that they turn out to be the same argument. But so with these arguments, you would say that, you know, a good operation should have two properties, two desirable properties with respect to what happened to the workspace. So one is that it should not increase the number of components in the workspace, because you want your derivation to eventually converge to forming a single sentence. And so you don't want to keep adding new stuff to the workspace and making it larger and larger, because otherwise you're not gonna, you know, converge to something. But at the same time, you want to not decrease the number of accessible terms, because you don't want to lose any kind of syntactic information. You don't want syntactic information to get destroyed in this derivation, and you want material that you have used to remain available for example, actions of internal merge, even once you form a single syntactic object at the end. So the way that this is phrased is, you know, workspace shouldn't increase in size, and accessible terms shouldn't decrease in number. So now there is if one counts what happens when you do, so for example, let's check that external and internal merge are okay. Yeah. So the way you count how the number of accessible terms changes, but the number of components is clear, right? Because, you know, if I'm doing external merge, I'm taking two components and I'm forming one of them. So my number of components is going down by one. So that's no problem. In the case of internal merge, the number of components is not changing, because I'm just moving one piece of a component back to itself. So that's clear. The number of accessible terms is a little bit more tricky to count because of this thing that I was saying last time of how you construct the remaining term where you cancel the deeper copy. And the counting is a little bit different with these two versions of that I mentioned last time of how you form the cancellation of the deeper copy, the one where you keep the trace and the one where you don't. Remember that the accessible terms of a syntactic object don't count the whole syntactic object itself as a component, but they count all the subtrees that hang from one of the other vertices. So the number of accessible terms that I have is the number of vertices minus one, because they don't count the one with the root. So in principle, if I take the number of accessible terms of the part that I've extracted and of the part that's left, those would add up to the total number of accessible terms minus one. But there is this other thing that when I cancel, like for example, if I'm extracting this thing, and now I have this thing left, but this vertex is no longer attached to anything, so it's really not there as a vertex anymore. So this is just this one. So I've lost one more vertex. So that's why there's a two here instead of a one. With the trace, you have different counting because this vertex remains as a new leaf. But okay, either way, it's just the numbers change slightly. But you can say that external merge with this counting increases the number of accessible terms by 2, and internal merge keeps it constant. And there's another two measures of size that I mentioned here. One is where you count the total number of vertices, meaning you count the sum of components and accessible terms. And those are the accessible terms of the whole workspace, not the accessible term of each component. And then there's this strange other sum of when you add the number of components one more time. I don't know what meaning, whether that has one can cook up some kind of meaning for that. The reason why I'm mentioning it is because this is a conserved quantity under external and internal merge. And it's exactly not a conserved quantity in most of the other cases. And so usually when you run into something that's a conserved quantity, you kind of ask what that corresponds to. And I don't know the answer. So if somebody has a good idea of how this.
Can you explain what a conserved quantity?
Yeah. So conserved quantity means that I'm in that table, I'm looking at how it changes, right? So external and internal merge don't change this quantity. But if I look at the other cases, so this is just saying that my counting of accessible terms is the one that's used among a bunch of other references. Where this version of the cancellation on time. And so, like, for example, I know this operation that I said that when you do internal merge, as I said, you first take out your accessible term. But as I said, this operation by itself, so it doesn't exist in isolation. And you see here, well, I said it because of this grading story that I said, but also because here you see that if you take it by itself, it would violate these rules about, because it increases number of components and decreases accessible terms, which is exactly the opposite of what you're supposed. But when it occurs in combination with an external merge to form internal merge, then this just gets exactly compensated and it gives the correct behavior. The other forms of merge, that's what I said, this conserved quantity. The other forms of merge, they essentially all violate this conservation. Well, except for this one of the cases of counter-secret merge. So I don't know what, I'm not sure what that means. That's like, well, somebody has some interpretation for this, that's nice. But so you see that all.
Can we see the two versions?
Hmm?
Can we see the two versions of the, like, 3A and? Yeah, just the two
Yeah,
versions of.
yeah. So this one, so,
Solid board.
yeah. Let me come back. Sorry. This one, yeah.
Oh.
So this one is the case where you're taking the same component, but you're taking two two, not one, so it's not like internal merge, where you take the whole component and you take an accessible term of that component. Here you take two accessible terms in one component, or two different ones. So, yeah, I don't know why this has a behavior. So it turns out that this kind of convolutional merge has a behavior that's more similar, but maybe this is not surprising. It's more similar to internal merge because of course you're inside one component. So maybe that's the reason why this one, in that respect, behaves like internal merge, but it violates some of the other properties. So, but anyway, if you look at these various size countings, you'll find that all the other forms of merge violate one or the other of these size counting properties. And so, you know, at the end of the day, right, so you can make a table, you know, is the size of the workspace decreasing? Yes or no? Is the number of accessible terms increasing? Or is the size non-increasing? Is the number of accessible terms non-decreasing? Is this total, you know, number, you know, bounded, you know, either 0 or 1, or is this conservation law conserved? And you see that, you know, any two of these will single out only external and internal merge as the right options. Okay, this and this other grading thing that I said before, as I said, they look different, but there's a way to combine both of them so that they become the same argument. And I might not have time to talk about that, but if you look a little bit later in my slides, you'll find that for how these two are, these two, you know, ways of selecting internal and external merge actually, yeah. Okay, so let me come to this issue of whether you have a issue of whether you can have an n-ary merge that's not instead of a binary merge. So what happens if hypothetically you would have a ternary merge or okay. So this would mean a different generative process for your syntactic objects. Now you would have a corresponding magma, non-associative commutative magma on a single n-ary operation. And your syntactic object would all look like n-ary trees. So it's the same thing, you know, you can count the union of all those that have a certain number of leaves. But the first thing that you will notice if you do this is that the binary trees are the only ones for which you can have any number of leaves. Any other n-ary merge will have a constraint on the number of leaves that you can have. You can only have, so if n is your n-arity of your operation, the only number of leaves that you can have are of the form some integer times n-1 plus 1. So this has this kind of very odd consequence that all your sentences would only be allowed to have a length that is k times n-1 plus 1. It's kind of a weird language. Okay, so this is why necessarily undergenerates, because you know you could take any syntactic object formed by binary merge, where the number of leaves is some number that's not of this form, 2, for example. So you cannot form any sentence of length 2, like it rains, not allowed. So it undergenerates.
So it undergenerates to pick an n other than 2.
Yeah, exactly. So I'm saying
Not
if you
to allow any n won't undergenerate.
no, of course, if you say I also have a binary merge,
Yeah.
then but then why do you need it?
No, but what you're saying is that if n was anything other than 2,
Yeah,
it would be in a
If you
weird
had a single merge
But
operation,
there's like a third possibility that's, you know, do this for any n.
yeah, there's a
Just pick
possibility
certain
that
number
you
of-
could have a binary merge and a ternary merge and so on. But then, you know, there's an economy principle that tells you why do you need all these other ones? Right? And that's, already, well, but there is also another argument, so this is the under-generation argument, right? And you can say, I can get around the under-generation argument by saying, well, I'm gonna have both the binary and the ternary and whatever. But there is an over-generation argument. And the over-generation argument, well, there's some things, well, okay, these other kind of phenomena are also depending on the fact of having, yeah.
Just before, just make sure I'm understanding. So if I have like a ternary merge, I mean, we have a vacuous object always, right? I mean, I can say here are three objects, A, B, and nothing.
Yeah,
And
but
that
nothing,
reduces to the binary case.
yes, so you have, say you have this empty, but then when you merge with the empty thing, you just get the thing that you start with. So if your thing is already, your thing is already of one of these lengths, if it's generated by an n-ary, and so you will not, okay, you will not get a new one, but it will still be bound by having lengths which are of these.
No, but so if my workspace has like it and rain,
Yeah,
can I apply a ternary branch to kind of say, okay, so find me it, find me rain, and find me one, like nothing?
yeah, but then that would be just, yeah, I mean, that. Yeah, so the answer is no, in the sense that, it's. You don't want to count that as being a lexical item.
So that's the assumption that there's.
That's.
Yeah.
So I meant if you take elements in your set of lexical items and syntactic feature, then you will only get things of that length. And of course, if you had only like an n-ary merge of some higher parity than 2, you would also have this thing that you would not be able to see certain ambiguities that you can see with the binary merge. But there is also an over-generation problem, not just an under-generation problem. The over-generation problem is already, there's something that Rodriguez wrote already some time ago, with empirical examples, that if you had a ternary merge, then you would also be getting some sentences that would not be grammatical with respect to a binary merge. So it would also over-generate, so you would get things that you don't want to get from a binary merge. And this is not solved by saying I have a binary and a ternary merge and the other thing. So the combination of the fact that it under-generates and it over-generates rules out the n-ary ones. Okay, so now so far, everything happens in this symmetric world where, the merge is, this merge operation is commutative, and my trees don't have a planar structure, and the leaves of the tree are not a set, an oriented, not a directed set. They're just. So the idea is that then, there is another process. So the generative process is happening in this symmetric world with abstract trees. And then there is an externalization process that actually, goes, so language that is produced in our brains at some point goes through our sensory motor system that forces us to impose like a time ordering in how we produce a sequence of words. And so this time ordering is forcing some planar embedding of these trees. And so I'm going to try to describe in the setting that we have how one should think of this externalization process that picks a planar structure for the trees. And the way I'm going to describe it is a kind of two-step procedure. And one of them, the first step is sort of, I'll explain why, is sort of taking a one-way street in the wrong direction. And the second step is killing off a lot of stuff. Okay, so let me go through these two operations and tell you why you need to do this, why you need these two things, right? So I'm gonna say that the first procedure is taking a section of a certain projection. I'll tell you what that means in a moment. And the second procedure is imposing a certain number of remaining constraints on what I get by this first step. Okay, so let's start from an observation about magmas and morphisms of magmas. So I said last time that our syntactic objects are the non-associative commutative magma generated by a single binary operation on the set of lexical items. You also have, so this object, the free commutative non-associative magma, also have the corresponding free non-commutative non-associative magma on the same set. And the difference between the two is that in the free commutative non-associative magma, you have a relation that you impose, which is the commutativity of the merge operation. In this other case, you don't impose even that relation. So it's even more free than the other person. It doesn't even have the commutativity relation. And this one is also a well-known generative process in that mathematicians, well, it's the generative process of the planar binary rooted trees with the leaves decorated by the set of lexical items. So the non-commutativity of this merge operation is what makes your trees planar, rather than making them abstract. Because now you can no longer flip, you have theta. Now this is no longer the same as beta, okay? As planar trees. They are the same as abstract trees, but they're not the same as planar trees. And okay, there is a canonical projection. So there is a morphism of magmas from these free non-associative, non-commutative magma to the free associative commutative magma, which is imposing the commutativity relation. So this is a very nice map. It's a surjection of sets, and it's a morphism of magmas. We're just forgetting the planar structure of the trees. This is all good, but there is no way to go the other way with a similarly nice map, because there is no morphism of magmas that goes from the commutative one to the non-commutative one. Because if you are mapping something commutative, what you get, and it's a morphism of to preserve the operation, then what you get should also be commutative. So, and the thing is that this non-free, because it's free, there are no relations, it contains no sub-magma that's commutative. So you have nowhere to map it so that it will stay commutative. Okay. So the problem is that, okay, we have this map. So that's this projection map that I described there, from planar trees to the non-planar trees, which is a nice morphism of magma, but it's going in the opposite way with respect to what I want to do with externalization. I want to assign a planar structure. I don't want to forget the planar structure. Okay. So what should you do with this? Right? So, well, the best thing that you can do is construct a section of this projection. What I mean by a section of this projection, I mean a map of sets, no, not a map of magmas, a map of sets from my commutative, so my abstract trees to the planar trees, that when I compose it with the projection, it gives me the identity like here. So what that means is simply that if I pick an abstract tree and I want to assign to it the planar structure, so that when I forget the planar structure, I get what I started with. Okay. So that's what the section means. It picks a choice in the fiber of the projection over my points. I choose one of all the elements will get identified together when I project them. And so it said, I'm taking a one-way street in the opposite direction. This comes with a penalty. And the fee that I have to pay for having taken my one-way street the wrong way is that A, I no longer have a morphism of magmas, and B, my construction is going to depend on a choice. It's no longer a canonical map. It's going to depend on the choice. So what these two things mean in linguistic terms. So the first one means that my merge can only act either before externalization or after externalization, but not both ways consistently at the same time, because I don't have a morphism of magmas between them. So the older version of minimalism were placing the merge on the planar trees, so non-commutative merge, using the non-commutative merge on the planar trees. The new version of minimalism is having the merge before externalization. These two things, you can have one or the other. You cannot have both of them simultaneously. That's the linguistic consequence of this simple observation. There's another consequence, is that externalization is necessarily language dependent. What you're doing when you're choosing this section is basically, you're only concerned that you want to be careful about is that the way you choose your planar structure is compatible with whatever syntactic parameter. Yeah.
All right, we're good.
Yeah. So if you want to make sure that the way you choose your planarization of trees is compatible with whatever syntactic parameters you have in a given language that rule word order properties. But other than that, no, you're making a choice. So you're making a choice that is language dependent. It's necessarily so because you don't have a canonical way of making this section. Okay, so that's consequences of these simple algebraic fact. Okay, so this is your first step. And now I'm saying that you have these other, so you come back for a second to this picture. You have this other thing that goes down, this one is a projection again, that goes down that other road. And what is that? Well, okay, now that I've just picked a planar structure for all my syntactic objects, and I've just done it in whatever way I want, as long as I don't violate word order structure of the specific language that I'm thinking about. Now I do have a lot of other things to worry about that I may be violating. There are other syntactic parameters that are not necessarily word order, don't necessarily have to do with word order, that I need to check whether my structures agree with or not. There are other things like theta relations, things like this that I need to check whether they are satisfied or not. So a lot of my syntactic objects a priori contain any kind of assignment of leaves of a lexical item of leaves. Many of them don't give me viable constructions that I want to keep. So I'm going to have to get down with a big quotient that kills off everything that's not consistent with the rest of the specific syntactic parameters and notion that I want to keep. And so this is the second step that I want to have in the externalization procedure. So okay, let me see where I am. Okay, so now. So just a simple observation that this idea of this kind of way of mapping something where instead of going from X to Y, you kind of climb up some map in the opposite direction from X to some other place and then go down the other way is something that in mathematics is called a correspondence instead of a function. Multi-valued functions are an example of that, and there's many settings in mathematics where these are the natural objects to consider when you are mapping something to something else. And so again, this construction is not strange. is just, an occurrence of this fact that functions are not always the best way of mapping things. And correspondences are often much better than functions. And this is an example where you have to do one of these things precisely because of this, absence of a morphism of normals in the other way. Okay, so I'm gonna skip a bunch of details right now. So let me just go through this. Yeah, okay.
What I'm confused about is what a section is.
Yeah. So, yeah, let me just say it like this, right? So suppose that I have two sets, X and Y, and I have a map, let me call it with the same name that I get it there, and call it Y, from X to Y, which is actually a surjection. So I keep everything in Y by X. But in general, if I look at what I have above a certain point in Y, I have a bunch of stuff.
Right.
So in general, no, this is not a single point, not injected, it's surjected. So what I mean by a section is, that I take a, map of sets in the opposite direction. And what I do is, I take a point here and I make a choice of one of these points above Y. So the conditions for the say is that if I go this way first and I go this way, I get the identity on Y. So I'm staying always on the fiber above Y. In principle, if I take an arbitrary
So the
function,
section will be a function.
a section would be a function.
Yeah, okay.
It would be a function, but it's a function that remembers the
That has-
structure, right,
Right.
of this
It
projection,
respects the
because
structure, yeah.
if I take an arbitrary function from Y to X, my image of Y could go anywhere in
Yeah,
X. That has nothing to do with this set.
right.
Okay, the coordinate that I want to land in
Got it.
so it's like Y, when I look at over here has an ambiguity. There's a lot of
Yeah,
points
so,
that end up collapsing to Y.
right,
And so I wanna just choose one of them.
Right.
And so in general, this thing depends on choice, because I
right.
have, so here we're working in a situation where this is a finite set, so there's no issue,
Yeah.
axiom of choice, whatever. But, in general,
Yeah.
having such a thing implies a choice.
Okay. Thank you.
Okay, so, let me start saying something which I think I have a lot, this part is a little bit technical, and I have a lot more stuff in the slides on this that I wanna, or I have time to cover, but I just wanna say a few things in general, and then next time maybe I'll see how much of it I can discuss, or maybe some things I might just not go into detail right now, and then if there's some time left at the end of the lecture, I'll come back to this in more detail, but we have in the second paper, we have like a kind of long discussion of what differs when you look at this point of view with, of algebras and so on, with this new version of minimalism, which is this strong minimalist thesis, strong minimalist thesis, and the sort of older versions of minimalism, particularly Stabler's, computational minimalism, which, I mean, it's kind of a maybe good comparison point because, that's been used a lot, and because it's also known that it has some, relation to formal languages and more context-free grammars and merged grammars and so on. So it's a form of minimalism that, a lot of people are familiar with. And so there's a natural question that, does this formalism apply to that setting too or not? And the thing is that, to some extent, you can, formulate that version of minimalism also in terms of algebras. And you notice two things when you do that there's two main ways in which these two ways of thinking of merge differ significantly. And the two main things that are significant is to the differences in the algebraic formalism. One is the fact that in the older version, you do only work with planar trees. So you don't have this symmetric part first and then externalization that planarizes the trees. You start directly with trees that are planar. That's one main difference. And the other main difference is that you have no workspaces. So you never take these forests, you always only work with trees, you never have the forest. And so what happens is that these two differences kind of combine together to make the algebraic formalism a lot more complicated. So you can kind of carry that over. There's still like a kind of hot algebra description. It becomes a lot more complicated than the hot algebra that I just described. And well, let me try to tell you the main reason quickly without too many details. Yeah, let me show you in this slide. So in the hot algebra that I described, some of you have already observed right away that the product structure is extremely simple, because my product structure is just assembling my workspace, taking a bunch of syntactic objects and put them together as the raw material that I have available for making the relations. And that operation is, as I said, commutative associative. It's very simple, has very simple properties. But now imagine that you don't have forests, you only have trees. So if I want a kind of product structure, I have to give you two trees, and you cannot just put them side by side, because that's going to give me a forest. You have to kind of combine them in some way, right? And get a new tree. And this is going to be also compatible with a co-product in which you disassemble these trees, and you should be able to see again in the co-product what you need to use for internal merge and so on. So it turns out that there is a way of constructing a hot algebra that uses only binary rooted trees and not binary forests. It's called the Voderonkov algebra, but the product immediately gets more complicated. So if I take a product of trees, I'm going to do it in this. So, well, the co-product is sort of trying to split my tree apart into two parts. But now I cannot do the cuts, because if I do the cuts, I'm going to end up with forests. If I wanted the co-product to be co-associative, I cannot just extract a single tree. So I cannot do the cuts. I have to sort of, pull apart my tree from the root to along paths from the root to the leaf. And that works. But if I want a compatible product now, I have to also take a tree, break it apart as I do for the co-product along paths from the tree to the root, and then graft each of these things on the leaves of the other tree. So this product is not commutative, and it's kind of very complicated. Like I have to tear apart one of my tree and then stack it on top of the other one. And the two sides of the product now play a very different role, not just the two sides of the co-product. And this is kind of the only thing you can do if you wanna if you wanna not use forests. So this is the argument for saying that at first, when you look in the at the presentation of the new form of minimalism, you say, why do I need workspaces? Okay, why can't I just use trees? What are they doing for me? But the thing is that they are simplifying everything, because if you are forced to always stacking together on a single component, your algebra is going to become unnecessarily complicated. So workspaces really simplify your algebraic structure significantly. That's why they're there. That's the actual underlying reason why you need workspaces. And so in stable minimalism, there is another thing moreover that you have. So this first observation is what I said: planar trees plus not having workspaces, and that combining, giving this much more complicated structure of object. There is another issue that of course, with the new minimalism, you throw it out of the door and will eventually come back through the window, which is the sort of labeling algorithms. But in the old version of minimalism, you kind of build those directly into the merge construction. And so on top of these other complications that I said, you have to do all this feature checking in order to be able to apply merge to begin with. And this, so there are all these label and you also have to keep track of the head structure, which is usually marked in this way, right? And instead of minimalism, you kind of follow the arrow to see where the head is going. And okay, so the external and internal merge themselves look similar to what they look in the case that we had. Again, you can think of it as admissible cuts and trees when you apply internal merge several times. You apply it once, it's a single cut. But those now, you have to relate these operations to the coproduct. The coproduct is not expressed directly in terms of this operation anymore. There is a way to express this coproduct in terms of these admissible cuts. And it is done. There's some math papers that explain how to do that, but they introduce a further complication, which is how to express these accessible cuts and remain in terms of the coproduct of this of one. So things get kind of very complicated there. And also this fact of having to check matching labels for applying this merge operation. This gives you a problem that these operations are no longer defined everywhere. They're only defined on domains where this matching happens. And when you start to iterate them, you have a compound, this problem compounds, right? Because you have to check domains for all the iterates. And so you get this kind of feature checking, and you can actually, we'll end with this. I'm going really quickly through this, but by the way, there's other issues which are the fact that this matching thing does not avoid certain kind of unlabeled constructions that are exocentric and don't have a good labeling. It is kind of an intrinsic linguistic issue, not a mathematical issue. But
So I just have a question, which is, so in my understanding of Stabler's Mill experiments and putting the features on the different flexible items was partially to address this issue of selection. So it wasn't just the case that you could sort of, always merge just two arbitrary lexical items together. So under what we're looking at, you can arbitrarily merge just any two lexical items.
yeah, and then you kill off at the end of this, this quotient map of the externalization is what kills the things that are not viable.
Well, that's what I was gonna ask. So so how exactly
Yeah,
is that?
so that's right. At that stage, you have to bring in some kind of a labeling algorithm
Right.
that, known as a paper, I think in 2015 or something. I forgot that, all these labeling.
No, I'm not in syntax.
But how to do this labeling algorithm for this new minimalism. So at that stage, you have to bring in something, but you do it after the fact, right? So your merge operation creates everything that it can.
Right.
And then-
filter later.
Right, so you don't have to actually do all this domain checking just to do the
Right.
merge. You
Right.
merge, you create everything that you can
Right.
with the merge, and then, there's some algorithm that checks whether this thing that you are getting is viable or not.
Right.
If it's not viable, you throw it away in that, and you keep what is viable.
So
I
is
mean,
there?
in a sense, of course, that's why I said that, it's an issue that you throw it out the door and it comes back through the window, because at some point you have to do that, right?
Yeah.
Sorry, can I interrupt? Because we have a class starting here
Oh, okay.
now. So,
Yeah.
yeah.
See, sorry, so well, I think we should stop here for today. I'll say a few more words about this, at the beginning of next time, but this is some of the main idea that, you try to separate these two issues.
Yeah.
And of course, the problem of having to check whether you have a viable labeling or not remains, is that you decouple it from the generative process.
Yes.
Rules here.
There's also, the workspace